Hello, I'm Jonathan Engelsma. This is part 8 in our tutorial on learning to program in C. In a previous screencast, we looked at arrays in C, and we saw how they could let us store a set of homogeneous data items and reference them with subscripts. Well, C also has a way to let us group together heterogeneous pieces of data in a single cohesive logical unit. We call these structures, or structs for short. In the remainder of this lesson, we're going to look at structs, which you can think of as sort of prehistoric classes if you already know an object-oriented language. And as we look at the syntax of structs, you're going to think, boy, this is kind of complicated and makes my C code hard to read. Well, we're going to introduce a very useful construct in C known as typedefs that give us some additional syntactic sugar to actually define structs and other non-trivial data structures in a more concise way. And finally, we're going to also take a look at unions. And you might be thinking, what are unions about? Better pay for programmers? Well, actually, not quite, but we'll have to save that for later. So arrays let us define a multiplicity of homogeneous chunks of data. Structs are kind of an analog or a very similar thing, only they let us group together logically related heterogeneous chunks of data into a single entity. And typedefs give us a nice syntactic tool to create what we can think of as aliases for types. And unions are kind of in a world all by themselves, and we'll look at that last. So here is the syntax for a very simple structure that I've defined in C. So we use the keyword struct followed by the name of the type. In this case, I'm defining a type location. So if I want to be able to handle locations in my programs, and locations are not just a single piece of data, but several related pieces of information, a struct is a great way to approach that. So in my case, the location consists of a character pointer to a description or a string, a description string, and then two floating point numbers, a latitude and a longitude, representing the geocoordinate of that particular location. In what follows, I've actually defined a variable of type location. The variable is called my_college, and I've even set an initializer to it, which you'll notice looks an awful lot like the array initializers that we've already encountered. So in this case, I'm specifying that the string pointer description points at a string GVSU. The latitude variable will be assigned 42.9709, and the longitude variable will be assigned the -85.8857. Now, it's important to realize that the first struct up there is actually the definition of the type location. It does not allocate any memory. That actually comes later when we define the variable myCollege of type struct location. In that case, the compiler will indeed allocate enough memory to store this piece of information. Now, going back to our concept of pointers, realize that that description variable there is in fact a pointer. So it's going to contain some 4-byte integer pointing off to the location that actually refers to the string. So the string data is actually allocated somewhere else in memory. It's not contained within the structure. The structure only contains a pointer, as I've demonstrated here. So let's put this structure location into context. So here you see the struct is actually defined globally outside of the functions and at the top of my C source file. This makes the type definition visible in all the functions that I define in this particular file. And if I wanted this type definition to be visible across multiple source files, I could actually create my own separate header file, a .h file, and put that type definition in it, and then I would include it in any source file that I'm writing that happens to need visibility to that particular type. Now, once again, note that this type definition in and of itself does not allocate any storage. That's not going to happen until we get down in the main routine and I've defined the variable myCollege. At that point, we now have the memory allocated to hold the values of that particular structure. Finally, notice that we can dereference or access the individual values in a structure by dereferencing the variable name, in this case, my college, followed by a dot or a period, and then followed by the data item name. So for example, my_college dot latitude refers to the floating point latitude value of the structure instance my college. Now we can also pass structures as arguments to functions, as you see here. And in this case, they're actually passed by value. So a copy of the data contained in the struct myloc, which is of type location, is going to be copied to the runtime stack. And once I get in the context of this function foo, I can go ahead and dereference the struct variable and access the individual pieces as I show you here in this particular example. I'm checking to see if myloc.description is not equal to null, and if it's not null, then I do a string comparison on it and check if it's equal to GVSU, the string GVSU, and if that condition is true as well, then I'm going to print out home sweet home. Now, structures, variables can be declared in the structure declaration. So in this case, I've got my struct location, and I've defined two variables of type struct location, and I've set an initializer for both of them. In addition, we can define functions that actually return structure values. So here's a function get_loc that returns a struct location to the caller. And finally, structs can be used in expressions and can be copied just as we've seen before. So in this case, I've got a input parameter of req, and I can do a string comparison on that. And if it's home, I'm going to assign some home location to the structure, to the local variable loc. And if it's not home, I'm going to be in the else clause, and I will do an assignment of cur_location. And what happens there is a member by member copy. So the values of the individual data items in the structure on the right end up getting copied into the corresponding values of the structure on the left hand of the equal sign. I can also nest structures within structures. So in this code example, I've got a structure called geofix, which contains a lat long. So I'm handling lat long as a single logical unit or logical entity. And then I go and I define a second structure, struct location, and I have there a character pointer to the description. And then notice that I've got a struct geofix called position or POS nested right inside my location. And similarly, when we actually define an initializer for this, we're going to use nested braces exactly as you see here. So very similar to how we initialized two-dimensional arrays. So references to the struct members must mirror this nesting hierarchy. So in this particular example, if I want to get at the latitude and longitude, I need to dereference that nested structure variable name. So in other words, if I want to access latitude, I need to say the location structure, which in this case is LOC dot, and the member that holds the lat and long is the variable with the name of POS. So I'm going to have a dot POS dot latitude. So I need to make sure that my references reflect the nesting hierarchy when I have nested structures. We can also have arrays of structures. So in this case, I've got my struct location, and I define a variable called check-ins to be an array of size 3. What this means is it's going to have an array which consists of 3 different locations. And you can see that I use the same syntax that we've seen previously to actually initialize this array with 3 structure values. So notice I've got a right squiggly brace, and inside that 3 structure initializers followed by a right curly brace. Now, the dereferencing of these arrays is exactly as before, so I'm going to have an index. So down in my main routine, I have a loop that prints these out, and you'll notice that I refer to the array check-ins sub I, but check-in sub I refers to the entire structure. If I wanted to print a particular value within that structure, say the description, I still need to use the dot variable name, in this case a dot description, after the array subscript. So let's talk briefly about typedef. So C lets us create aliases for data types using this typedef construct. And the syntax is quite simple, as you see here. I want to have an alias for type int called clock with a capital C. So I can do that by writing out typedef space int space clock. And what we're telling the compiler is, hey, if you see a variable that has type clock with a capital C, just know that that is a regular old integer. Now, it might not be clear how this is advantageous with the example I've chosen to use here, but as we'll see, typedefs are particularly useful when we're working with structs. But we can typedef anything we want, including arrays. So I could have a typedef car buffer 1024. So anytime I define a variable of type buffer, it's an array of 1K bytes. So here I have a car B1, which is an array of 1024 bytes, and right underneath it you see a definition buffer with a capital B, B2. In this particular case, that statement is equivalent to the one above in terms of the variable types that they define. So B1 and B2 are of the same type. We can also use typedefs to define pointer types. So I could have a string, which is a car star, defined as follows. I have a typedef space char space star string. And what this is basically saying is string with a capital S is the same as car star. So when I say car star str1, I'm defining a string pointer, and my last example on this screen, string with a capital S str2, is basically defining a variable string2 with the equivalent type to string1. It's just a character star. So in general, you can remember how to define typedefs by remembering these 3 simple steps. So first of all, just write down the statement as if a variable of the desired type were being declared. So you're going to proceed just as before. Type name space variable. And where the name of the declared variable would normally appear, go ahead and substitute the new type name or the alias, and then go over to the left and in front of all that, place the keyword typedef. If you follow these 3 steps or you remember these 3 steps, you'll always know how to do typedefs of the types that you come up with in your C program. So let's talk about unions. A union is actually defined with almost the same syntax as a structure. In essence, a union is going to let us store different data types in the same memory location. Hence, only one of the member variables in a union can be used at the same time. The compiler's going to assure that there's enough memory allocated for a union variable to hold the largest individual element that it could potentially store. So in this particular example, if we assume that a character takes 1 byte, an integer takes 4, and a double takes 8, a variable of type union indecision, as we defined it here, is actually going to be allocated 8 bytes because by definition that is the largest individual data item in the union. But keep in mind, we're not storing, in this example, a character, an integer, and a double. Instead, we're storing a character or an integer or a double. And we need to kind of keep track in our program logic what kind of information we store in a union variable, so later when we dereference and pull it back out again, we're accessing the same kind, because there's actually one piece of memory allocated, and all of the different union members, data members, are going to use that same member, or same memory. So unions are used by more advanced programs in C. Even if you're not using them in the programs you're writing, you'll want to be familiar with the syntax, because a lot of the C code that you'll be reading that others have written will indeed use unions. So let's look at some code examples. Let's begin by reviewing the syntax of defining structs. So I'm going to create a program called struct1.c, and remember to define a structure. We're going to start by using the keyword struct, then the name of the structure type, followed by a left curly brace. Then we'll type in the member variables of the type. So if I want to do description, as we talked about it moments ago, I'll have these three values. And finally, I'll close it off with a semicolon. To define a struct, I'm going to use the keyword struct, type in the name of the struct I'm referring to, and then the name of the variable. To initialize it, we'll use the same, very similar syntax to what we used for arrays. And to reference the individual data elements in a structure, I'm going to use the dot syntax. Okay, let's give this one a try and compile it and run it. Oops, I have a typo. Good enough. Let's look at another example. Let's go ahead and take a look at how structures get passed by value in C. So I'll start with my previous program. And let's add a function called foo that takes a parameter of type struct location named myloc. And let's make this function modify one of the values. So we'll have it change myloc.latitude to 0 and longitude. Then we'll go ahead and call this function. And then we'll print the value. So the goal here is to see if the actual value, my college, passed to this function gets modified or not. And in this case, you can see that the values I set in the function did not change the structure that was defined out in the main. So we can see here that that structure is being passed by value. In the function, we were operating on a copy of the one that was defined in main. Let's look at a third example. We'll start with our previous. And let's initialize a couple of variables right here, a couple of global variables. And this time we'll have our function return the value being a struct, and we'll have the input string be just a character pointer. So if the input string equals home, we're going to simply copy the global variable home location into the variable loc. And if not, we'll give loc cur location. And finally, we will return loc. Okay, so then we're going to call this function passing in the string current. And what we want to see here is that when we first call this function, the variable myloc, which is a struct location defined in main as a local variable, is uninitialized. When I call foo, and I do need to assign the value, it returns a value, and then when we print it out, we're hoping to see the value that was assigned cur location above. Oops, we've got an error. So in this case, sure enough, the return value actually gets copied on the call stack and stored in the local variable myloc in main, as you can see by the values that we've printed out here. Let's look at yet another example. Let's take a look at structures within structures. So to do this, I'll start with my original example. I'll introduce a new structure. And I'll add a structure within my location structure. And let's go ahead and put an initializer on here. And to initialize that inner structure, again, I'll need a brace. And then I'll put the values. And if I want to print that value out, then I need to reference description just as before, but latitude and longitude are now part of that inner or that nested structure. So I need to be sure that my dereferencing follows the hierarchy here. So I need to use that variable POS. Hit a little typo there. Okay, sure enough, it works as expected. Let's look at a final example that compares structs with unions in terms of how much space the compiler allocates in memory to store them. Okay, so you can see a difference here. So foo is 16, fudge is 8. So if we go back to our original program, you see I used typedefs there, but everything is exactly the same in the definitions, except I use struct in one and union in the other. But the max size of these three is the double, of course, and those are 8. So in the case of the union, 8 is the largest. So the size of that union is going to be 8 because it only allocates enough for the largest. On the other hand, when we look at the foo, that was actually 16, and you might be wondering, how did it come up with that? Because a car is only 1 byte. So you're thinking we should have an integer which is 4, a car which is 1, which is 5, and then a double. You're thinking we should have 13. Well, what happens is the C compiler likes to align stuff in memory for reasons we won't get into right here. So there's actually 3 bytes of filler to pad out that car so that it's actually on byte boundaries. Hence, the size of foo, type foo with a capital F, is 16, and the size of fudge, the union here, is only 8. Make sure you understand the differences between these two concepts, struct and union, and what's going on here with the compiler.